This problem is on section 3.3. The question says TMA manufactures 37 inches high definition LCD TVs in two separate locations, location 1 and location 2. The output at location 1 is at most 6,000 TVs per month, whereas the output of location 2 is at most 5,000 TVs per month. TMA is the main supplier of televisions to the Pulsar Corporation, its holding company, which has priority in having all the requirements met. In certain months, Pulsar placed orders of 3,000 and 4,000, 3,000 televisions to be shipped to City A and 4,000 to be shipped to City B. And the shipping costs per dollar, in dollars, per television from the two TMA plants to the two Pulsar factories are shown in this table. Now the question is how to minimize the cost function. So we want to minimize this function and then find the minimum cost. So in order to solve this problem, it's better to make some graph that explain the relationships between these data included in this question, or information introduced in this question. So we have two locations. We have location 1 and we have location 2 to manufacture this type of TVs. And the products should be shipped to factor in a city A, let's call this city A, and to some factor in city B for Pulsar Corporation. Now we have some information here given in this problem. We can read here that we have 6,000 TVs per month produced from location or output of at location 1. So we need now to define some variables. Let's define some variables this way. We want to send some TVs from location 1 to city A, and here if you read, we want to send 3,000 to city A, and 3,000, this will come from location 1 and from location 2. So we have 3,000. Let's say that location 1 will send X items, X TVs. Location 2 will send 3,000 minus what was sent from location 1. So that means 3,000 minus X. For example, if location 1 sent 100, then location 2 will send 3,000 minus 100, and that's 2,900. Okay? And from location 1, we want to send some TVs to City B, to factor in City B, and we want to send TVs from location 2. If we assume that we send Y items, Y TVs from location 1 to City B, then, and we know that we want to send 4,000 TVs these should be shipped to City B, then we have 4,000 minus what was shipped from location 1. So this diagram will help us to understand the relationships. So X denotes number of TVs shipped from location 1 to city A, and Y represents number of TVs shipped from same location 1 to city B. After defining these variables, now we know that we have number of TVs required by the two factors A, B are 4,000, 3,000 and 4,000 respectively, and this will help us to make these relationship. Now after that, we want to write the cost function. Here, if you look at this table, it includes some costs. For shipping from location 1 to city A, each item costs $6. For shipping from location 1 to city B, each item costs $4. For sending or shipping from location 2 to city A, each item costs $8, and to ship to city B, each item costs $10. So we need to use this because we are talking about the cost here. So we need to define the cost function as our objective function. So let's denote it as C. This is the cost function. So how to define C? We know that for C we have $6. Let's start with location 1 here. So we have $6 for each item shipped to city A and $4 for each item shipped to city B. So from location 1 we have X items shipped to city A, X items, and each item costs us $6. And we have Y items shipped to city B, and each item costs $4. Similarly, for location 2, we want to find the cost of shipping from location 2. So we add that to the shipping from location 1, and here shipping costs for location 2. Now for location 2 we send 3,000 minus X to city A, but that costs $8. So we write $8 times how many items? 3,000 minus X are shipped to city A. Plus, and when we ship to city B, we ship 4,000 minus Y items, and each item will cost us $10. So we multiply by $10. And then we simplify this function. So we have 6x plus 4y plus 8 times 3,000, 24,000. And 8 times negative x, negative 8x, then 10 times 4,000, 40,000. And 10 times negative y, negative 10y. And then we simplify more. We have 6x minus 8x, that's negative 2x. And we have 4y minus 10y, that's negative 6y. And we have 24,000 plus 40,000, that will give us 64,000. So this is the cost function, and it represents the objective function, because the objective function is the function that we want to maximize or minimize, and here we want to minimize the cost. So this is the first thing to find, the main function or the objective function. Now we need to look at the constraints. For the constraints, we know that number of items here, if you read here, location the output of location 1 is at most 6,000. So from location 1 we produce X and Y, and the sum should not exceed 6,000. So it will be less than or equal to 6,000. So this is the first inequality. And we have also 3,000 plus 4,000 minus Y. These come from location 2, that should not exceed 5,000. It's at most 5,000. So from location 2 we produce 3000 minus x, and we produce 4000 minus y, and that should not exceed 5000. So this is the second inequality. And we can simplify the second inequality for sure. We have 3000 plus 4000, that's 7000. We have negative x, negative y less than or equal to 5000, and then we want to get rid of the 7000 on the left hand side of this inequality. So we subtract 7000, we get negative x, negative y less than or equal to negative 2000, and then we multiply each term by negative sign because we want these to be positive. It's better to write them as positive. So multiply each term by negative sign, you get positive x, positive y, and this inequality symbol will be reversed. If it's less than, it becomes greater than or equal. If it's less than or equal, it becomes greater than or equal if we multiply by a negative sign. And then the right hand side becomes 2000. I dropped all negative signs and I flipped the I reversed the inequality symbol or inequality sign. Okay, so this is the second inequality or constraint after simplifying it. So we have this constraint, this constraint. We have other constraints. We know that x should not be negative, and y should not be should not be negative, because those are non-negativity conditions. X is number of items, can be 0 or positive, but it can't be negative, and the same thing for y. So this is number 3. Okay, now we have linear program, complete linear program. We have c equals negative 2x, negative 6y plus 64,000. This is the objective function. And we have subject to the constraints are the following. We have x plus y less than or equal to 6,000. And we have x plus y greater than or equal to 2,000. And x greater than or equal to 0, y greater than or equal to 0. Now, this is the linear program. This is linear program. It consists of the objective function and some constraints. Now we want to solve this because we want to minimize the costs. Now in order to minimize the costs, we need to graph the region. So we start with the constraints. We have the first one, x plus y is less than or equal to 6,000, and here we make a table. We set x equals 0 and y equals 0, and then we find the corresponding values. When x equals 0, let's write this as an equation. So this is x plus y equals 6,000 in order to graph that line. So x is 0, that means y equals 6,000. And when y equals 0, x equals 6,000. And that means the point is 0, 6,000, and 6,000 and y, and 0. Y equals 0. For the second one, we have x plus y greater than or equal to 2,000. So we make it an equation. And then we have xy, which is 0, 0 here. When x is 0, y equals 2,000. And when y equals 0, x equals 2,000. So the 2 points are 0, 2,000, and 2,000, and 0. And we have x greater than or equal to 0. That means to the right of the y-axis, and y greater than or equal to 0, that means above the x-axis. Now I think we still have some constraints about x and y. So if we look at the problem itself, we still have some constraints. We said that the order is 3,000, consists of 3,000 to be shipped to city A, and 4,000 to be shipped to city B. And that means any one of the variables. So we ship to city A here. So 3,000 should be shipped to city A. And that means, so here we have the variable x, right, included here. So x cannot exceed 3,000. So x is less than or equal to 3,000. We need to add this constraint here. X is less than or equal to 3,000. And we know that the place order for city B, we need to ship 4,000. So we want to ship to city B for 4,000, and we have here y and y here. The variable is y, so y cannot exceed 4,000 in this case, right? So we have the constraint y is less than or equal to 4,000. So we need to include those conditions. So make sure that you study each type of the include all data or all information from the question and find all possible constraints on the variables. Okay, because we said here x is greater than or equal to 0, but it should not exceed 3,000. Y is greater than or equal to 0, but it should not exceed 4,000. Now, what happens if y, for example, x exceeds 3,000? Let's say 4,000. If x exceeds 4,000, 3,000. Let's say 4,000. Then we have here 3,000 minus 4,000. It becomes negative 1,000, and that's impossible to have negative number of items. Okay, or the number of items should be positive or non-negative, at least 0 or positive, but it can't be negative. Okay, so these are all the constraints. Let's graph this constraint. So we have x less than or equal to 3,000. So we have a vertical axis, and less than, that means to the left, and y less than or equal to 4,000, that's horizontal axis or horizontal line, and below it. Okay, so we'll see this from the graph. Now let's graph the region, the feasible solution region. Here we have y, here we have x axis. Now we have, let's start with the first point, 0 and 6,000. Let's say it's here, 0 and 6,000. And we have 6,000 and 0, let's say it's here. And now we connect them with a straight line that represents x plus y equals 6,000. And now we want to see if the solution is above or below this line. We test 0, 0. So if we plug 0, 0 here, it's still less than or equal to 6,000. That means the solution will be under this line. And for the second one, let me use this color, green color. We have 0, 2,000. And we have 2,000, 0. And we connect them with a straight line, and this is the equation for equation x plus y equals 2,000. Now, is the solution above or below this? Let's try 0, 0. 0 plus 0 is greater than or equal to 2,000. This is not correct, so that means the solution will be the opposite side of that line. I mean, the opposite region. It's not the region that includes 0, 0. And then we have other constraints. We have here this condition here, x less than or equal to 3,000. So let's graph x equals 3,000. Where's 3,000? 3,000 is here. This is 3,000. And now x equals 3,000, that's a vertical line. And less than or equal to 3,000, that means to the left. And let's graph y equals 4,000. 4,000 is here. And now we graph a horizontal line. And so this is y equals 4,000. And this is x equals 3,000. And it's below this line because it's less than or equal to 4,000. Y is the height, is less than or equal to 4,000. So as you can see, now we still have two other constraints. X is greater than or equal to 0. So x is greater than or equal to 0. That means to the right of the y-axis. And y is greater than or equal to 0. That means above the x-axis. Now the region becomes this region. Sorry, I included some. Okay, let's do it again. This region here. Okay, so after determining this region, this is the region S, So let's call it region S. And now we need to determine the vertices. The vertices of this region are 2000. Let's make a table here with the vertices. We have 2000, and we have this vertex here. This is 3000. We have this vertex, but we don't know the coordinates of this at this point. So how to find that? We set the two equations equal to each other. Let's do it here. So it's the intersection of the blue line with the brown line, which is x equals 3000. So we just plug x equals 3000 to get y equals 3000 as well. So this point here is 3000. So we put it here. We have 3000 and 3000. Let's continue. And we have this point here. We don't know this point as well. So let's find this point. So this comes from the intersection of the blue line, which is x plus y equals 6000. This is the equation. With the y equals 4000, the brown line. So since we know that y, we can find x, it's 2000. So the point is, this point is 2000 and 4000. So we put it here, 2000 and 4000. Now let's continue. We still have other two vertices. This vertex is 0, 4000. And we have the last vertex is 0 and 2000. So we got all the vertices of this region. Now we want to see which one gives us a minimum value for the cost function. The cost function is 64,000. We can write it starting with a positive number, 64,000 minus 2x minus 6y. Now let's plug the values. We plug x equals 2000 and y equals 0. This will give us, using the calculator, you can compute this. You get something like, double check here. We get 60,000. And let's plug 3000 here, x 3000 and y equals 0. This will give us 58,000, and 3000 gives us 40,000. 2000, 4000 give us 36,000. 4000 give 40,000, and 2000 when x equals 0 and y equals 2000, this gives us 52,000. Now if we look at these points, which point gives us the minimum value? The minimum value is this 36,000. This is the minimum cost, and this corresponds to x equals 2000 and y equals 4000. So let's back to our diagram. The diagram was, let me do it again. So we have location 1, location 2, and we have city A and city B. Here we have x, here 3000 minus x. So we should produce how many send or ship how many TVs to location A from to city A from location 1. So we plug 2000, so we should ship 2000 from location 1 to city A, and we should send, if this is 1000, x is 2000, then we get here 1000. 3000 minus 2000 is 1000. So we get here 2000 should be sent from location 1 to city A, and 1000 should be sent from location 2 to city A. And what about the other location, to other city. So this is the equation here is y, and here we have 4,000 minus y. So y in this case is 4,000. So if we plug 4,000 here, so we have 4,000 minus 4,000, that's 0 TVs, and here 4,000. So in order to minimize the costs, to get the minimum cost of 36,000, we should ship 2,000 TVs from location 1 to city A and 1,000 TVs from location 2 to city A. And we also need to ship 4,000 TVs from location 1 to city B and 0 TVs from location 2 to city B. This will minimize the cost function.